Section 5.2, Systems of Linear Equations, Unique Solutions, Day 1. Usually I break this up into two different class days. Of course, now you can look at this at your own pace as long as you keep up with the assignments in WebAssign. So first thing we're going to look at is what is an augmented matrix. Well, it is a matrix, which is what? Well, first of all, a matrix is just an array of numbers. So this is an example of a matrix. It's specifically called an augmented matrix because it consists of the coefficient matrix, which comes from all of the numerical coefficients that you see in front of all your variables. So you can look at those numerical values in front of the x, y, and z here in this system of linear equations, and then compare it to those numbers. Note, they're the same. And then the next thing is the column of constants matrix. So all the constants are aligned in a column at the end. All right, so with that being said, let's see if we can start off very basic. And let's rewrite these systems of linear equations as augmented matrices. So the first one would look like this. Open bracket. And then your column, So for this first one, we're looking at the coefficient matrix and then the column of constants matrix. All right, so 1, because it's 1x, then 3, because it's 3y, and then 4, because it's 4z. And then we're going to put a dividing bar there, and then we're going to put the 7. So this is your first row of your new augmented matrix based on this linear equation. And then you're going to continue to do the same thing for the remainder of this. So 2, make sure you leave a little bit of a space in between your numbers so it doesn't look like just one number. And finally, we have rewritten this system of linear equations into what's called an augmented matrix. Again, this is a 3 by 3 coefficient matrix, and this would be a 3 by 1 column of constants matrix. And let's take a look at this example. So coefficient of x would be 1. There's no y, so you put a 0. Then you put a -3. Put the bar there. -5. And then so on and so forth. It's fascinating. Riveting. Rich. Okay, so we've completed those two examples, going from a system of linear equations into an augmented matrix form. And that's what you're going to have to be able to do to start the systematic approach we're going to be looking at here in a little bit in terms of solving these larger systems. But let's keep going. Before we get into that, what we're going to do now is go the other direction. So if you're given an augmented matrix, you should also be able to write this in the form of a system of linear equations. So this one would be what? This one would be 1x plus 2y plus 3z equals 11. This would be 0x plus 2y minus 4z equals -6. And then finally, -x plus y plus 2 equals 2. And there's your system based on this matrix. One more. This one would be 1x plus 0y plus 7z. Note, I left a little bit of a space there, equaling 17. And then I'm going to not put anything under the x because there's a 0 right there. And then the y stays here, 1y minus 2z equals -3. And then we get 0 x's, 0 y's, and then plus 11z. Really didn't need to put that plus there, but it's fine. Is equal to 22. And that is how the second system of linear equations would look. Okay, the next thing we want to look at, and this is the big thing coming from section 5.2, is what is called Gauss-Jordan elimination method. All right, so this is the systematic technique we're going to be looking at that will allow us to solve systems of linear equations of any size. That's the key there. I mean, of course, we can solve smaller types. We could even solve a system of 3 equations and 3 unknowns. But we want to learn a process that not only will help us solve a system of linear equations, but will also help us with other concepts that will be presented in this class in chapter 6. So we need to learn what are called row operations. There are 3 row operations we can perform that make up what is called Gauss-Jordan elimination method. So the first one is you're allowed to interchange any 2 rows. And actually, let me just go ahead and show you. I'm going to make up a system here. And I'm not going to write it as a matrix. I'm just going to show you that you've done this before. But it will, of course, look different to you because of the new notation and because we're looking at it in terms of a matrix. But the first one is you're allowed to interchange any 2 rows. You've always known that. I mean, wouldn't you agree that if you looked at this as a system of linear equations and you actually solve this for x and y, well, you get the exact same result if you interchange these 2 equations and rewrote it like this? I just switched the equations. It's not going to change the answer, is it? No. All right, so that's one row operation we can perform. Okay. The second one is we can replace any row with a non-zero constant multiple of itself. Okay. So we can replace any row by a non-zero constant multiple of itself. What does that mean? Well, here's what that means. If we go back to this example I just made up, do you agree I could multiply this second equation by a -2 and then rewrite the entire system as what? Well, the first linear equation stays the same. And then the second linear equation becomes -6x minus 8y is equal to -4. Again, the result, if I were to solve this system, would be exactly the same as the result I would have gotten if I left it just like this. So again, you're allowed to multiply any equation by a non-zero constant. And the last thing you're allowed to do with respect to row operations is replace any row by the sum of that row and a constant multiple of any row. That sounds like a lot, but really the gist of this is what I'm getting ready to show you. You're allowed to add 2 equations together in order to help you solve that system. So again, things that you've done before are making up the row operations that we're going to be looking at in terms of Gauss-Jordan elimination method. So you're allowed to add these together. You'd get -y equals -3. And then here again, if you wanted to, multiply both sides of this by -1, and you get y equals 3. And then, of course, at this point, you'd have to plug in what you got for y back into one of the original equations to get your x value to be spit out. That's not going to be the case when we look at solving these systems using Gauss-Jordan elimination method. So that's the next thing we're going to be looking at. Just some things about that first. So real quick, this is what will be happening. And again, you're going to learn this process by hopefully understanding what I'm presenting to you in terms of the notation and the techniques. And it's just going to take some repetition to get this down. I'll also be showing you how to perform row operations with your graphing calculator. That'll be in another video. Okay, so the first thing is what's going to happen. You're going to be given a system of linear equations, and you're going to be responsible for handling something of this size. All right, so this would be a 3 by 4 size system, which would be rewritten in terms of an augmented matrix, again, of 3 by 4 size. Our goal is to rewrite this matrix into what is called row reduced echelon form, or RREF for short. So to do that, we will use the Gauss-Jordan elimination method, which again, I will go over with you several times, to ultimately get our matrix in this form. All right, so again, we started with this, and then a lot of row operations are happening throughout the process of Gauss-Jordan elimination, and we end up getting this. Now note what that means. This matrix is really giving us our solutions. We don't have to use any substitution or anything. This is going to be called the identity matrix. It's just a diagonal of ones going from the upper left to lower right, and then zeros everywhere else. These values are actually our solutions. So note that this means 1x, no y, no z equals 3. So in other words, x equals 3. In this one, no x, 1y, no z equals 1. So y equals 1, and so on and so forth, z equals 2. So the solution here is actually called an ordered triple, and the ordered triple would be 3, 1, 2. No longer an ordered pair based on the size of the system. It's again called an ordered triple. Okay, so these are the guidelines for putting something in what's called row reduced form, or what something does look like in row reduced form. Again, I'll be explaining all this by way of example as we progress through the notes.